So thank you, everyone. This is one talk from the series of the Artificial Intelligence Laboratory here at the Institute of Computing. The lab is known as Recod.ai. And today I have the pleasure to have my friend here, Luis Lamb, from the Federal University of Rio Grande do Sul. Luis is one of the fathers of neural-symbolic AI, and he is the most adequate person to talk about this topic. It's been a while that I wanted to have him to talk to us, but he is like a very busy man. Thank you, Luis, for accepting the invitation. Luis is a professor, as I said, in the Federal University of Rio Grande do Sul, and his main interests include machine learning and reasoning, neurosymbolic computing, logic in computation, and artificial intelligence, as well as cognitive and neurocomputation, AI ethics, and social computing and social problem solving. He is a CNPq researcher 1A, which is the highest grade that we have in Brazil. And currently, he is the Secretary of Innovation, Science, and Technology for the state of Rio Grande do Sul. So, Luis, thank you very much. And without anything else, I give it to you. So please feel free to share your screen and start your presentation. Normally, we have about 50 minutes for presentations and 20 minutes for questions.
Okay. So thank you so much, Anderson. It's a great pleasure to be here, to be talking to so many friends. And let's start. Let me see here. Just a second. Okay. Just confirm if you can see it.
Yes, we can see it.
Okay. So I'm apologizing in advance for being very tired today, but let's move on. So it's my fault, not anyone else's fault. So we are seeing some a very interesting, very profitable, very peculiar time in AI and computing research. We are experiencing a time where the very large corporations, very large companies have advanced the case for artificial intelligence and for topics that in the recent past were seen with some skepticism. And some of these topics include some of the ideas and the history of what we are going to tell you today here in this talk. And they involve, for instance, the idea of using neural networks to express logical reasoning, or to use logical reasoning to explain neural networks, or even more off the track, that would be a combination of the two ideas, of the two paradigms that have been defined and have been discussed, have been investigated by two separate communities. So this is the overall idea here, to tell you a little bit of what's going on in this field for a long time. I've seen other people here who have worked in the field. I've seen my friend Priscilla from Rio. I believe that she was here, she was around here, and that she's been working in this field as well for a long time. So it's very nice to see that we have other people that work on it. So the background here is it's a famous picture that describes the importance of knowledge just before the Renaissance. And we know that we are seeing these times now. We are also going back to a few concepts in science and technology, even the idea of using neural network models that were seen with skepticism, as we said, just over 10 years ago. And we are now combining two fields here in neurosymbolic AI that sometimes are not very well understood. But since some companies, some large corporations have put forward the case for neurosymbolic AI, this has attracted some attention of people in several research communities. And I'm going to give you an overview of the field since over the last 2 decades, let's see. Just to tell you, that's not something that came out of the blue. It's a very new thing where very novel ideas just came out of nowhere. No, it's not the case. It's something that has been developed over some decades. So the main objective of this topic is to give you some general concepts about the relationship between connectionism and symbolism, of the relationship between learning and reasoning in AI, that they're separate, they're clearly separate communities and separate interests, and also to make the case that perhaps neurosymbolic computing, neurosymbolic AI can help to bridge these two fields and bridge this gap between symbolism and connectionism. So thanks to many collaborators, many friends over the years, and we have recently wrote a paper on the evolution of the subject that is better than this talk to actually understand what's going on in the field. It makes much more references to other topics too, and in a paper you don't have the time restrictions to talk about everything. So thank you so much to many students and collaborators over the years, in particular to Artur and to my PhD students and master students. And the idea here in AI, and I use this slide for when I'm talking to people outside AI, you know, the idea is to build processes, build technologies, build machines, build computers that perhaps can mimic our behavior in terms of learning and reasoning and perception and other cognitive abilities. And this comes from one of the early questions that even Turing thought about. But if you go even further back, mathematicians, some brilliant mathematicians from previous centers were trying to find ways of automating reasoning, automating logical inference and logical calculations. And we are now living in this time where computer science is not seen only as a tool anymore, and the IT departments of corporations are not seen as cost centers or places where you have to invest some money to get some better management of the corporation, but they are the core of every business initiative, every initiative, every project that the company, that the corporations do, no matter the size. They always think about how the role of technology will improve, will leverage this kind of new perspective of company. But going back a little bit to AI, we have seen extraordinary facts, historical points in history where we've seen the prominence of and the domain of data, and the huge amount and the large number of people using more and more technology, more and more, producing more and more data. And you know, of course, that this has given rise to the big tech corporations that are now the dominant force in several domains of our lives, and they are achieving $1 trillion market valuation, market capitalization, and so on, market cap. And AI is also at the back of this developments at the back. And we have seen some signals over the years that AI, that computer science, that technology is dominating our lives. It's very clear now. It's dominating even the cultural scene. It has influence over political decisions. It dominates how people behave in society. It influences even electoral procedure, electoral processes all over the world. We have seen several issues in cybersecurity that are clearly very important in terms of a geopolitical and a corporate perspective. But with all these wonderful technologies, all these wonderful tools, we still have a lot of challenges that remain to be tackled, several challenges. And several of these challenges have to do, in a way, indirectly or directly, to this kind of research that tries to bring one of the important aspects of computer science, and one of the important aspects of science, that's the interpretability issue. We have to be able to interpret why science produces some results. one has to understand, and then we can make a very easy analogy here. You want to understand why some vaccine works, why some drug that has been developed to treat some illness, some disease, some medical condition works. You want to understand what's underneath these technologies. But when we move to some of these models, when we move to these very large models that we have today in AI, one thinks in terms of how can one interpret, how can one verify, validate this kind of models. And this is related to several important issues in computer science, in very deep technical questions, not only questions that are related to business decisions, to decisions that are taken at a higher level. We are also dealing with issues such as fairness, such as trust, ethical consequence, and also the notion of causality. And what we want to bring to the fore here is that deep learning has delivered extremely important results for every subfield of computer science these days. We've seen a large number, and the increase of published papers in computer science perhaps is only smaller than the increase of number of people who claim now to be doing AI research these days. And so AI is becoming a technology that perhaps will become a common tool that will be used across disciplines, across several economic sectors, and it's becoming an horizontal or a vertical technology, depending on how the author of these definitions of vertical or horizontal or interdisciplinary or ubiquitous technology defines AI. And when we have this developments over the last 10 years in deep learning, we have to bring also some of the memories. I remember that in the early 2000s in machine learning and AI conferences, and Priscilla is here. I know that Priscilla has worked on neural networks for a long time too, as myself. It was very rare to see neural networks papers in machine learning conferences. You can check it. It's very easy today to check this information. Look at the proceedings of the main AI conferences and the main machine learning conference between the year 2000, 1999, 2000, and 2006, 2007, and count the percentage of papers that were published on artificial neural networks. And then neural networks came, and the advantages of using these deep networks, or the deep networks developed by Hinton and other pioneers, were made clear in image processing, in computer vision, in natural language processing, machine translation, and other fields. But more recently, people started to think about how to assign meaning to this kind of constructions. And in computer science, in computing, in any field that's based in mathematical formalization, one also seeks not only efficacy, and the right level of abstraction, but one seeks to understand what actually a model is modeling, if the model is predictive, how the model works, what's the behavior of the model, how the model behaves in different situations, and even more so when one is producing a technology that will take decisions, as we and as AI researchers claim that AI is going to take decisions for us, or will be partly responsible for taking decisions. One wants to understand what's inside this so-called black boxes of AI. And this has brought to the fore then recent developments, a lot of attention to neural networks and symbolic AI, and how symbolic AI could be used to understand the reasoning processes, and how symbolic AI could perhaps be used to understand and explain what's going on in terms of neural networks, neural learning. And this has then came to the fore, and we are talking about this subject here. We're talking about neurosymbolic AI, because over the last 2 years, I have to say, since the late 2019, November, December 2019, and over the year 2020, now 2021, Some companies have defended the need for neurosymbolic techniques and using neurosymbolic AI as a means to streamline this integration between learning and reasoning. And some very important researchers, including deep learning pioneers, including Nobel laureates such as Daniel Kahneman, who wrote very famous bestsellers like Fast and Slow. He also wrote about errors, and he writes about human reasoning. He's a very accomplished psychologist and economist. And also other influential researchers are now asking themselves, well, we are dealing here with a lot of data that is represented in a symbolic way. And we have this interplay between symbolic reasoning and machine learning. How can one possibly integrate these two fields? And so this gave rise to some concerns, but also to some interesting novel results, some interesting cooperation, some interesting debates, some interesting tweets, right? Because today everyone is on Twitter, presenting their results and their papers. People now publish papers on archive and announce their papers on Twitter and other media. And this debate about logic and machine learning has reached, let's say, the mainstream discussion in AI. And one way of thinking how one can build an analogy or build a relationship between these two subjects is to make the parallel that people have done with thinking fast and slow, as put forward by Daniel Kahneman and people in AI, people in computer science. Well, very fastly and not very slowly, very fastly, very quickly made the relationship that machine learning would be the fast thinking and logical reasoning would be the slow thinking, the reflexive way of thinking about some new problem and using your knowledge to reflect upon the information and then finally taking some decisions. Okay, this is relatively new. And we're very glad that in the first AI debate between Yoasha Benji and Gary Marcus, we're very happy and very surprised that Gary Marcus has mentioned our work on from 2009, our book that was called Neurosymbolic Cognitive Reasoning, where we had put forward the case for formal integration between neural learning and logical reasoning. This was, of course, done in the spirit of combining these two cognitive abilities. Has a very interesting relationship with integrating the statistical nature of machine learning or statistical nature of learning, the uncertainty that is involved in dealing with huge amounts of data, with these huge data sets that we have today, and how one could relate to the reflexive nature of reasoning, the construction of hypotheses based on very well-established logical rules and logical axioms. How could one relate these two topics? And there is some other interesting aspect here is that we have always defended that neural learning and symbolic reasoning should be integrated. And we are quite surprised that even Daniel Kahneman said in the AI 2020, it's on record on a very interesting debate, on a fireside conversation with Daniel Kahneman, that he said that as far as he's concerned, system one, that is the fast way of thinking and taking decisions that people are making analogies with machine learning, certainly knows some kind of language, and system two, in his opinion, does involve certain manipulation of symbols. And then as researcher, our role has been to investigate how these two things are related to each other. And I'm just going to skip this slide about the evolution of AI and the symbolic and the connection in schools. By now I have talked a lot about them, but we can go back some time about it. And the motivation about building neurosymbolic system is that learning comes from information, comes from change in the environment, comes from adaptation. However, in AI, what we see is that learning actually comes from a lot of data that reflect such changes in the environment. when we are training our bases, we're dealing typically with more static data, not in a dynamic way. And to reason about common sense knowledge using this kind of data makes the challenge even harder. How can one think about a common sense decision making like a baby does here? This is the picture of my daughter when she was very young, and she observed how the way that we brush the teeth of her teeth, and then she imitated the process and reasoned upon the information that she had and tried to imitate the process in the first doll that she had. So, and then I made this of course, every AI researcher does this analogy with child learning to reason, children learning and child learning to integrate learning, reasoning, action, and information that they abstract from the environment, generalizations. And this integration between learning and learning in AI is a big challenge. We cannot say that this is very easy, because we know from a computational point of view that reasoning can be something very hard to implement in computational systems in computer science. We have several challenges that lead to very important questions, deep questions in the field of computer science related to computational complexity, related to descriptive complexity, and to mathematical logic, as we know. But in order to develop this approach, we followed, in our school of neurosymbolic AI, we follow what we call a foundational approach. That is to say that our component in neurosymbolic AI, the symbolic bit comes from logical formalization, from fragments, using fragments of logical systems, and trying to teach learning algorithms to reason upon such logical rules. And we try to mimic logical rules. We try to use these logical rules to represent the reasoning process. For those who have never worked on automated theorem proving or knowledge representation and reasoning, there are very sophisticated algorithms that not always have to do with the way that we build inference in our brains. They are built in a way to make the computational process more efficient. But when we are trying to build here systems, I'm going to show you that in some way, we are also trying to model the way that people reason using logical rules, using very simple logical rules. And then one comes, well, okay, this guy is talking about his own motivation. Is there any other grounds for that? One of the early defenders of the integration of learning and reasoning was no less than Les Valiant, who is a Turing Award winner, and he's the proponent of PAC learning and of several other very important contributions to computer science, and he has defended over more than 20 years that there is a need for integrating reasoning and learning in a sound way. And if you want to use sound reasoning, the way to do it is to use, or at least to pay attention to, the way that logicians have developed logical reasoning rules over the last 2,000 years and over the last century in computer science. And also people ask, well, is there any application of neurosymbolic AI? Yes, there are applications of neurosymbolic AI. Some authors claim that everything is neurosymbolic. Some authors claim that when you are doing simple neural learning over a lot of data, people say, well, look, numbers are symbols. We have this huge data set. This data set is represented by some pixels. Pixels are mapped into zeros and ones, and so everything is a symbol, and then we are doing neurosymbolic reasoning, neurosymbolic AI. Okay, that's not the spirit, but people claim that everything, some people claim that everything is neurosymbolic, but that's not the point that we are going to make here. Yes, there are applications, the applications are listed in our paper, and I'm just going to skim over them, but now let's go to some technical aspects. Well, from the beginning, when one thinks in terms of using logic for something, one thinks in terms of the simplest logic that there is, that everyone learns in high school or learns in the first years of their undergraduate degree. People think, well, logic is that thing about propositional logic, is the and or operators, is the other if thing that I don't know why it makes sense to comes from something false and concludes that something is always true. And so let's think about implementing simple propositional logics in neural networks. So it turns out that during the 90s already, people were working on building neural networks that would be capable to compute simple logic programming constructions, simple fragments of logic programming. And there are several competing approaches, including the well-known approach from Jude Shavlik in the US. There is this well-known approach by Brazilian guys, by Arthur Garcês and Gerson Jabrucha from the Federal University of Rio, called CILP, which was a system that integrated learning in let's say, in logic programming and logical inference using neural networks. And there are some important results that they proved that they even found ways of formalizing how neural networks would perform logical reasoning. And they also proved some interesting results, such as that for any logic program P, propositional logic P, it was possible to construct a neural network that would compute the result of this program, would compute what we call in logic programming the fixed point semantics of such a program. So this led to other constructions during the 90s. These constructions were very useful because they were shown to work very well for their purposes. Of course, we did not have GPUs or the massive amount of computer power that we have these days in our offices or in the cloud or wherever, or in any research lab. But they were very successful in showing that, yes, of course, we can show that there are correspondences between fragments of logic programming, fragments of first order logic, fragments of some other fuzzy logics, and some neural networks that one can construct. So there was these groups here in Brazil. There was a group in the United States led by Jude Shavlik that built the system known as K-band, that stands for Knowledge-Based Artificial Neural Networks. Is a very highly cited paper. There are some papers by a German group too, led by Professor Hodober, and they were interested also in seeing if these massively parallel models of computation called neural networks would have any relation with parallel processing, building very efficient machines to AI. Let us remember that this was probably an influence of the Japanese fifth generation too, because the Japanese were using massively parallel computers, were building very fast computers. And so computer science at that time, 30 years ago, was very different from computer science today. People were interested in solving problems that had a different scale. However, I'm going to develop these ideas further because these ideas are coming back now. And another question that we ask, okay, we can represent the simple logics, propositional logics, or we can represent clauses or fragments of logic programming. But can we think in terms of representing, for instance, knowledge that evolves in time? As we mentioned here, as we mentioned before, machine learning is pretty much about adapting to new information that an artificial agent, a robot, a system, an AI tool sees again for the first time, or sees for the first time, or again and again and again, sees these databases with some very small changes over time. So the notion of time, the notion of knowledge evolution in time is also very important to consider. And already in the 90s, there was a school of thought led by very famous American logicians. And they published a very influential book in AI about reasoning about knowledge, where they show how one could represent the knowledge, the interaction between multi-agent systems, and how agents in AI would exchange information. And the way that they formalize the interactions between agents or multi-agent systems in AI was using a logic that is known as epistemic logic, the logics of knowledge. And in a way, this was also very, very weird because, wow, these are guys bringing concepts that philosophers study, and philosophers, they don't think about very concrete programs, and these guys are putting forward the case for using modal logics in artificial intelligence, modal logic to explain properties of distributed systems, of artificial intelligence systems, and so on. But turns out that modal logic, and people sometimes forget it, modal logic has several branches. Modal logics has several interpretations, and one possible interpretation, of model logic is known as the possible world semantics that was put forward by a famous philosopher called Saul Kripke in the late 50s. Kripke wrote his first paper on model logic when he was 18 years old, and he defined the semantics of modal logics, and modal logic turned out from the late 70s to be extremely important in computer science. Modal logics, and in particular temporal modal logic, underlies and is the basis of every modern model checker and several formal verification tools that have been built and even have led the development of temporal logics in computer science, have led to another Turing Award winner in the name of Amir Pinueli and another Turing Award winners in formal verification. So this is a logic that's very important in terms of dealing with computational processes. And so it was natural to us, if we're going to represent the knowledge and how knowledge evolves in a learning procedure, to use the appropriate logical tool and trying to relate this logical reasoning tool, this logical reasoning machinery, this logical reasoning abstraction in the form of modal logics, and try to teach the neural network models to reason about the interactions between agents, reason about the knowledge of agents. And it also turned out that, I'm going to skip some technical details to not to make the talk too boring. It also turned out that modal logic was quite interesting to think about distributed systems. There was, if one looks at the procedures of the conference on distributed computing in the 80s and 90s, there are several papers on modeling distributed test beds, on modeling, for instance, the dining philosopher's problem, on modeling other problems that are used as test beds in distributed computing using this kind of machinery. And here, in terms of using neural networks, we're able to show for very simple, using very simple neural networks construction, that it was possible to represent fragments of modal reasoning, of modal logic with the framework of neural networks. And why is that important? That's important because then we can move towards a more formal approach to represent in a formalized way how the knowledge of an agent, how the knowledge of a system, how the learning procedure of an agent can evolve in time. If one makes the analogy of building intelligent agents with the analogy of the school of agents that put forward the case for modal logics in multi-agent systems, one can see that this is a very appropriate tool to represent the relationships between agents exchanging information. And one thinks in terms of modeling modern learning systems. Of course, computer science today is all about interactions, about billions and billions of people, processes, and tools exchanging information on the web, and knowledge of these tools and the knowledge of these agent systems, the knowledge of the systems that we're building is evolving and increasing all the time with more and more information. So it seemed to us that it was very natural to represent modal logics in neural networks. And so we are able to produce some results, some theoretical results. And these results, for instance, we showed that we could compute this well-known test beds used in distributed computing, and they have these funny names in computer science, like the Weismann puzzle, like the Muddy-Truden puzzle. Other puzzles are more related to probabilistic reasoning, including the Monty Hall puzzle, that's well known, the one that you open the doors and asks for someone to either change or stick to his choice or her choice, and so on. We're able to represent that the knowledge evolving in time could be represented or formally represented in neural networks. So here, the key idea, the key insight was to see the neural networks as possible worlds or as possible states. And in temporal logic or in modal logic or in epistemic logic, we have this notion of possible world semantics that was put forward by Saul Kripke in the late 50s. And it's used today in computer science, 60 years later, in formal verification and model checking and so on. And the key idea here, the key insight was to understand that some particular neural network could be either represent the knowledge of one particular agent, or one could build networks that in a way that they would represent possible worlds. And in possible worlds, and let's us interpret this possible worlds as a possible state. As in a state machine, one can claim, one can state that these states or these possible worlds, they represent the state of knowledge of the world of a particular agent at some point in time, or they can, for instance, they can represent the information that the system has when it reaches that state. So this analogy is very clear that one can make. And then we're able to do what we wanted to do. That was actually to represent the logical inference rules, formalized logical inference rules within neural networks. Of course, in order to do that, you have to translate these rules to the neural networks. Okay, so we used a translation algorithm that used this information, we use several examples to train the networks, and I'm going to go back to that later on. But the idea here was not only to see if the system could be efficient, but it was also to see if one would be able to construct neural networks that would mimic in a way the way that people reason, the way that mathematicians reason when they are building. And some of these rules that we built, they were based on a system of deduction system called natural deduction. And we used that on purpose. Why didn't we use another algorithm that people used in automated theorem proving? Well, we use natural deduction on purpose because that's the way people reason. We wanted to see if it was possible in a limited setting. Of course, the reasoning rules are sound. They're not always complete. It's a logical concept that we can talk a little bit later, but we are able to represent these rules for modalities, rules for reasoning about knowledge evolution within the neural network framework. And in order to represent that, we had a translation algorithm that would then build the networks with, for instance, the program that we wanted to train the network. And how this thing worked? This thing worked by using a translation algorithm that implements the logical reasoning rules. And we present several examples, of course, and use cross-validation to run the experiments. And by using cross-validation, one can test and see if the system is learning to reason about several information. And what we can report here is that we are able to solve several examples. Here we have just for a pictorial representation, we have a representation here in this, let's call this three neurons, N1, N2, and 3, and they can be understood or interpreted as possible worlds. And then we have algorithms, and we have a way of using the logical rules as inspiration and using this translation algorithms in a way that allows one to represent how the logical implications, or how the logical conjunctions, or how the other logical operations, logical formula are represented in the states where these formulas should hold, in the states or in the possible worlds where these formulas hold true. And by using logical reasoning rules, one could train the networks to understand or to learn how to proceed later on with novel examples on how to deal with novel examples and present new inferences. Okay, and here is an example of the details that we have in the papers about how to translate, for instance, a temporal logic based on the previous time operator. We use this kind of construction also to represent for instance, the several problems that involve temporal reasoning, including examples from software engineering. We have some papers that have been applied to typical software engineering test beds and so on, and also to very classical puzzles, as the one I mentioned, the 90 philosophers, the evolving philosophers, and so on. And another intuition that we can have here is that this systems allows you, for instance, represent in an ensemble of neural networks, or in a relation between these possible worlds, one can build a mapping between the symbolic representation and the connectionist representation of the rules. And of course, I have to stress it again, that in order to represent the logical reasoning rules. You need an algorithm that does all the dirty work in terms of how one can build the connections between the weights, the connections between all those parameters that we have in the neural networks. But the pictorial representation here gives you an idea about, for instance, in the Monty children, how the children that are related in this problem relate to each other. It's actually a distributed problem-solving problem that we are able to train the network and show that the network can learn to solve this kind of procedure. And moreover, we have some formal results that, for instance, when one thinks in terms of logical reasoning that involves a temporal dimension, it can be, for instance, a linear temporal logic or a kind of temporal logic programming system that's an extension of logic programming with a temporal operator or with temporal predicates, no matter what. We're able to represent that for a model or for temporal logic programs, we are able to show how to construct neural networks that would correspond to an engine that would compute the result of these programs, that would converge the fixed point of these programs that we presented as input to the neural network. Okay, this gives you a general idea. And here we have another example that are explained in the papers. As I mentioned, the Monty children puzzle is a very classic puzzle that was made even more famous in computer science by these very prominent logicians, computational logicians, Ron Fagin, Joe Halpern, Moshe Vardi, and Yoram Moses. And they wrote this book that became the standard book on logical reasoning in multi-agent systems. And we use these test beds for distributed knowledge representation as test beds for neurosymbolic AI systems too. Okay, so this was the key idea that we had in this foundational papers. And the idea of this picture is that we are able to represent how knowledge evolves in time. Of course, you can think in terms of unfolding time in a very large system can lead to some combinatorial explosions, but we can go back later on to talk about how to solve these issues too. Another thing that we did was to check, okay, you have solved this very theoretical problems, these problems that only logicians like yourself or formal verification guys or computational logicians are interested. Can you use this system? Can you use neurosymbolic AI to any application outside the domain of toy problems or the domain of problems that only are of interest to logicians or to theoreticians? Okay, and then what we did, and this is almost 10 years ago now, I get surprised that how time flies, but this thing has given rise to some recent interest in the last couple of years. We can give you the points later on. What we are able to show is that we can use what we learned from representing temporal logic in neural networks and use it as a tool to integrate this kind of knowledge with symbolic model checkers. What we did here was that we are able to use, in a nutshell, the information or their counterexamples that a model checker gives you as possibilities for refining the specifications or refining the models of your system. So initially, what we had in this approach was that the initial model is subject to verification, and if the model does not satisfy the given properties that are specified in a temporal language, a set of temporal counterexamples is returned. And this is a characteristic of a model checker. Typically, model checkers give you counterexamples when you are using these tools. And so these counterexamples can then be used as input to what we called in software engineering as the adaptation engine. So this adaptation engine translated the knowledge and adapted the knowledge that we learned to refine the model that we are using for as an input to the model checker. And then here, what we can do is to use an integration between machine learning and formal verification using exactly the philosophy of neurosymbolic AI. that is using knowledge representation integrated with machine learning, with a machine learning algorithm to improve a system and refine a description of the system and then produce better quality software. And recently, this paper was published by David Harrell et al. At AAAI 2019 has put forward an approach that's extremely similar to this approach of ourselves that is titled Labor Division with Movable Walls, where they compose executable temporal specifications with machine learning and search. And they use exactly the same principle of using the counterexamples to refine the process of the models that are used in the model checker. Okay, so this gives you a technical idea of what has gone in the early ages, but now we have to see what people are doing these days. So what are the potential applications? What are the use of, what's the main use of neurosymbolic AI? How can one build this principal approach to build new tools? How one deals with this duality? Does it actually make sense to consider neurosymbolic AI as a solution to some problem? Okay, well, there are several challenges that one has to think. First is that the first thing that one has to consider is that first are the logic and higher order knowledge and higher order logics are prevalent and they appear in several applications of computer science. If one thinks in terms of specifying a very large system or verifying systems or reasoning about properties of systems, one has to deal with relations, with relational reasoning, and as a consequence for relational learning. So one has a big challenge here that is, for instance, to explain the models, to explain what's going on in neural networks and how one can explain the models that we are building in deep learning using, for instance, first-order logic as a tool, and how the first-order logic can be integrated to neural networks. And what I have to say here is that IBM has recently published a paper on a system based on first-order logic reasoning. This is a state-of-the-art problem that IBM is tackling at the moment. You can check on arXiv. It's a paper called Logical Neural Networks by a large number of researchers from IBM, and they are doing exactly that. How can we represent logical neural networks? How can we use the appropriate embedding techniques so that we can represent it or use a distributed neural network to represent relational knowledge that would correspond to first-order logics that are needed in applications. Another very important open question, very important challenge that one has in computer science, and this comes from criticism, for instance, from cognitive psychologists, come from criticism from people who work on natural language about how to deal with common sense reasoning in an efficient way and in a way that makes sense. And also another research topic that has come to the fore recently is the use of graph neural networks and graph neural models or several convolutional graph networks in a number of applications. One interesting application of graph neural networks related to symbolic AI and symbolic reasoning was the representation of efficient combinatorial reasoning. How can one deal, for instance, how can one solve typical combinatorial problems in computer science that are highly relevant in our field, including satisfiability, including the TSP problem, including graph quarreling problem and other problems? How can one show that neural networks can, in an effective and principled way, solve this kind of problem? We have some papers on this subject that are also dealing with some of these state-of-the-art problems, and of course we can expand on it later on. And finally, when one thinks in terms of these applications of large language models, let's say no-code programming, text generation, text summarization, when one thinks in terms of the applications that tools such as GPT-3 will have in the near future, we start to think about, wow, what's the behavior of the systems when we consider human network communication or human large language model communication or human foundation model communication, as the Stanford group has put forward. how can we consider here using some knowledge from multi-agent systems? How can we use, for instance, the notion of human argumentation and communication with AI systems to establish protocols for human users and artificial agents to ask questions that make sense, to check the understanding of the systems, and to actually check if the output of these systems that are using vast amount of data, that are using, billions and billions, hundreds of billions of parameters these days, over 100 billion parameters that we have seen recently. How can one assign a semantics, and how can one ensure that, can one assure that the output of these systems actually has a mathematical meaning, has a logical meaning, and has a well-founded semantics. Also, what we want to do here is to build systems that, in the end of the day, understand each other, understand ourselves, and what we want to build here is systems where we are understanding what they are producing, and one can explain to ourselves, to scientists, to other computer science, the meaning of the behavior of those systems. Because in the recent debate, what we have seen is that the representation of knowledge is still an open problem. People are still trying to understand the best way to represent knowledge. So, and people are still trying an even harder problem, is how to assign meaning to the logical inference that we make using, for instance, very large language models or very recent results in deep learning that give us a plethora of results that are extremely useful, but sometimes one cannot begin to understand how they reach these results. Okay, so in summary, I could talk for much longer. I didn't have time to speak about everything I had to in these 50 minutes, but what we are doing in neurosymbolic AI is to try and build a principal approach to combine logical reasoning and machine learning. We know from computer science, we know from the first class in computational complexity that reasoning is very hard in computer science, is hard to achieve. And to teach a machine to reason using a machine learning algorithm is an even harder, more complex task that one has at hand. And we know also from observing the world that reasoning is hard. Some people have lots of difficulties in making logical inferences and make sense of what's going in the world. So when one thinks in terms of neurosymbolic AI, combining, for instance, relational reasoning, combining full predicate reasoning, which is, by the way, undecidable, one has to think in terms of alternatives. And if I was not clear enough, another reason that one can look, for instance, to modal logics is that modal logics, technically, they go beyond propositional logic. They correspond to some fragments of first-order logic. And they also allows you, for at least for some relational reasoning, given the possible world semantics of the topological semantics that modal logic have. So that's a possible way to look forward to further developments before going to full scale or full throttle to full predicate reasoning in neural networks. And of course, there are several ways of interacting with this community. There are several ways of learning what's going on in this field. There is a workshop series called the Neurosymbolic Workshop Series since 2005. The next workshop will take place, well, of course, it will take place nowhere. It's a virtual workshop in October, next October. There are several conferences that are now home to several workshops on integrating machine learning and reasoning. Here I have listed some of the recent workshops at NeurIPS. And there is a lot of information these days about how one can build neurosymbolic models and how can one understand what's actually going on in this field. So I have only scratched the surface. I apologize for being way too long here, sometimes not very objective, but we have lots of dualities in science, such as the wave-particle duality, the mind-brain duality, the symbolic, sub-symbolic debate in cognitive science, in neurocomputation, the continuous and discrete maths duality in mathematics, and so on. But if we work towards integration in science, towards building richer models, one can reach very interesting results, outstanding results that, of course, will make our lives in this planet much better. So thank you so much for the opportunity. I would have a long list of bibliography to share with you, Anderson, but I can send you the presentation, or you can check the references in the archive paper on neurosymbolic AI that probably soon will be so-called formally published in some journal. So thank you so much. I didn't have time to everything, so I decided to give you a few pointers to the literature and explain to you how the field started, because I am sometimes seeing things these days where people are missing where science has come from and the origins of the field and all the work that has been done in the past. So thank you. It's a great honor to be talking at your university. That is one of the top universities in Latin America, in our country, and has a large number of extremely competent, friendly, and friendly researchers. Thank you so much.
Thanks a lot, Luis. The presentation was awesome, and I would like to receive the slides later to share with everyone. Thank you. I have a lot of questions, but as a good host, I will give first the pass to people here in the audience. So please, guys and girls, if you have questions, please type them here, and I will start with one until you type yours. So, Luis, there are a lot of discussion in terms of the singularity and the common sense representation, and Kurzweil says that by 2029 we're going to have it, basically using deep neural networks or whatever. But Gary Marcus on the other side, for instance, thinks that we are in the wrong path. We definitely need to merge much more knowledge to have something like that. So what's your opinion on the singularity? And what's your opinion on the state that we have now in terms of common sense representation in AI?
Okay, thank you. Well, I'll start by the letter. In terms of common sense representation, from my experience, and there are lots of other competent researchers here, we haven't found the proper way to represent already yet common sense reasoning in order to teach machines to learn about common sense. Let's see, I don't know if I was clear. For instance, I am very happy to see developments in terms of large language models. I'm going to start to use the API. I'm very happy to see developments in terms of codecs and everything that's coming now. But in terms of common sense, when we try to run very simple examples in neurosymbolic AI about common sense reasoning, then we get to the point where we see how hard it is to train a network to display some sort of logical reasoning. It's significantly easier, for instance, to do some of the algorithms that we did to teach the networks to learn to make logical inference in temporal logic or in model logic, or even more so in propositional logic that's been studied at least since the 40s. The first paper by McCulloch and Pitts was about representing propositional reasoning and or operators in neural networks. Nobody reads these papers. I read them, kind of a computer science and archaeologist. So I read all these old papers. AI. I read all these old papers, and I believe, and Jacques is here too, I believe that we haven't found the appropriate way first to represent knowledge towards common sense reasoning or common sense learning. Okay, we don't know yet. We don't know what's the way what's the best tool to represent knowledge. What neural networks and deep learning are very good at is, of course, huge amount of data, and identifying very hard patterns to find in this large amount of data. Of course, I'm oversimplifying, and I am pro neural networks. Okay, I am pro neural networks. I was once accused at a conference of using neural networks when neural networks were dead. I was there in 2003 at a very large, very important AI conference when someone told me neural networks are dead. Why are you using that? Okay. So, but what I have to say here is that Jacques is here. He opened his camera because I was provoking him. And in my opinion, and I come from the logic school too, we haven't found the appropriate way to represent knowledge towards common sense reasoning. Common sense reasoning is still an open problem, very hard open problem. And the tools that we have today, they have not shown common sense reasoning yet. So in order to move towards singularity, find a way, first we have to find a way to properly represent human knowledge or common sense knowledge towards learning it and towards deep learning. So we haven't found this yet. We haven't found the appropriate abstraction for knowledge representation in massively parallel large language models, let's say. They're very good for some tasks, but not for common sense reasoning yet. Okay.
Thank you.
So it's still a long way to go until singularity. Okay.
I completely agree with you. And this is what I've been talking to my students. And I definitely don't agree with Kurzweil when he says by 2029. Definitely no. So Jacques, it's a pleasure also to have you here today. So the stage is yours. Please go ahead.
Thank you very much. Luis, it was a great pleasure hearing you and seeing you again after so many years.
My pleasure.
2 years ago, we saw each other at the beginning of the pandemic or just before the pandemic.
Yes. Yes.
Anyway, so the other pleasure was, to hear modal logic. I started my PhD on modal logic, and then I had some students working with it, then I dropped totally, no logic for me anymore. Anyway, so let me ask you, I know of two other lines of neurosymbolic reasoning, neurosymbolic convergence. And I wonder if you could at least mention what's the state of the art. One was extracting rules from network, right? Gerson had something on that a long time ago, and I don't know the state of the art on this one. But another one, I think Gerson also had. Gerson was the only one I knew was about starting a neural network with a logic programming and then learning from examples and changing, right? So the symbolic part as a starting constraint, but could be overridden by learning through the process. If you could at least tell me what's the state of the art of those at least two other lines of research, please.
Okay. Very good, Jacques. Things are in a way sort of reviving, let's say. There is a revival. This system called Logic Neural Networks by IBM reminds me a lot of the work that Gerson has done in the 90s, okay? It's slightly different because they have a kind of fuzzy interpretation and fuzzy mapping of the predicates. They map to a kind of fuzzy logic, semantics, the predicates, okay? It's called Logic Neural Networks and is being put forward by IBM. In terms of the second question, what we have to think about here is that today people are using a lot of let's simplify tensor computation or tensor-based models, where they transform the symbolic representation into a vector space where the reasoning is kind of matrix computation over distance functions, okay? This makes a lot of sense for deep learning people. They use more or less the same process that deep learning uses by representing this symbolic representation into a vector, and then they map this vector to tensors and use, of course, this very large machinery and operations in the end of the day to carry out the procedure. And in another way, you can also think that the logical or the predicates or the prologue system that Gerson was doing was a kind of representing these relations in a localized neural network. It was not, let's say, it was not exactly distributed neural network. It was more localized. It's more, let's say, he had a system where he had an algorithm that translated the predicates to the network, and then he built the network, and then he processed the program, and then he computed the program, he found the fixed point of the program, the result, and in the end of the day, he also used an extraction, or he and his collaborators use an extraction mechanism, pedagogical extraction mechanism, to extract a kind of, let's say, a logic-based symbolic representation of the extraction mechanisms. But today, what we have seen is a lot of work on in this school on inductive logic programming, and the interpretation that people are using to the networks is the relational interpretation and the relation extraction using, let's say, a way, or using the classical way that ILP people use. But there is another thing that I have to mention here, Jacques, that perhaps the main school of formalized symbolic reasoning in neurosymbolic or in symbolic AI now is focused on graph neural network models, because people found ways of solving combinatorial problems or combinatorial optimization problems using the graph neural network structure, using the message passing mechanism that's very basic in GNNs, the so-called GNNs, and then you have graph convolutional networks, graph neural graph attention networks, and so on. Some people have extended these models to solve image processing models, but in terms of the symbolic way, perhaps what you would have to look at in terms of state of the art, and this is highly influenced by people like Yosha Benji and his group. They're also looking at graph neural network representation for combinatorial problems. And graph neural networks have been used because they have a lot of relationships with important problems in computer science. You know, as old guys, you know that when you find a graph representation, then you relate, for instance, to bin packing, to TSP, to graph coloring, to all those problems in those classical books. And then you start to think about, well, how can we learn to reason about, how can we learn to solve this kind of problems that am I going to be able to be the guy who will find a way of using deep learning instead of simplex, or deep learning instead of Dijkstra algorithm, or deep learning instead of the best SAT solving that there is in the SAT competition? Or am I the guy who is going to solve constraint satisfaction instead of using 30 years of constraint satisfaction algorithms and so on? I'm gonna use this deep learning model here that okay, so the state of the art is pretty much looking at these tools of solving combinatorial optimization. That's what I would say in terms of state of the art at the moment.
Thanks a lot.
Yeah. Well, there are many schools. You know, machine learning is now a huge area. Yep. So I'm thinking in terms of foundational problems in computer science, like logic, combinatorial optimization, graph problems. But if you look in natural language, today, people that are building inference models in natural language processing, in machine translation, in natural language application, they are starting to say that this is neurosymbolic AI too, because building a semantics to natural language processing is now considered to be a neurosymbolic AI subfield or related field too. If you are building interpretation for, or image interpretation, for instance, in computer vision, you are saying that this is neurosymbolic AI. Okay, I'm very happy that they're calling it neurosymbolic AI, because you are trying to assign meaning to image understanding, right? Anderson is a specialist in this field, and it's legitimate in my opinion. If you're trying to find a semantics for visual information processing, for visual inference, it's legitimate that you call it a neurosymbolic approach if you are using symbolic tools, logical tools, or partial order-based model or algebraic model. Of course, you can map that into a neurosymbolic perspective.
Thanks a lot, Luis, and thanks, Jax, for the question. I have some questions here. This one from Thiago. I have seen work done on symbolic regression getting great results, mainly on physics problems with Feynman AI. How does this relate to neurosymbolic AI, if it's possible?
Can you just repeat the problem? We are on the web. There was a
Okay.
There's some noise in your connection. Just
Thiago is saying that he had seen some great results on symbolic regression, and mainly in physics problems. For instance, with Feynman AI, Richard Feynman AI. So, do you know if there is a relationship of this kind of approach to neurosymbolic AI?
Let me tell you something. I had a very bright student who studied phase transition in neurocomputation and computing decision problems, for instance. At least there is a decision in terms, there is a connection in terms of phase transition between the combinatorial problems and physical and problems in physics. Okay, so there are connections too that one can exploit. There are physicists working on symbolic representations of problems in physics. If you think in terms of quantum logics, there's a very strong relationship between quantum logics and quantum mechanics and so on, and people, of course, building computational models for learning quantum computing and so on. And over, let's say, about 2 decades ago, people were studying phase transition of satisfiability and of combinatorial problems, and they found very interesting relationships with the foundations of physics. So yeah, there are connections. Yes, you can find for it. I'm not investigating that. I don't have the time to, but I have seen papers establishing these connections.
Very good. Alexandre Ferreira is thanking for the presentation, and he's saying that in the early 2000s, he used semantic nets for representing common sense knowledge.
Yeah.
These nets are highly based on k-thematic relations from Minsky in his book, The Society of Mind from 1986. Do you think that Minsky's k-thematic connections could contribute to neurosymbolic AI?
I think so. I think they could contribute to it. The key aspect here is that in computer science we are, and even more in machine learning, we are always seeking efficiency. If we're not seeking efficiency, we are seeking universality or generality. Okay, be as more general as okay. You are not very efficient, but you are very general. So I think this is an interesting approach that deserves to be studied. Yeah, I think so.
I have now one question from Paulo, which I'm gonna complement with one from myself. So he's asking if is there any kind of automatic extraction of rules and knowledge representation possible to neurosymbolic AI. I think that what he's asking is, suppose that we have a solution that's deep learning based, and we trained it with a bunch of data, and we have this solution. Is there a way of extracting rules from this kind of solution that's already made? Or in other words, is there hope for a model that's already constructed, and I want to use neurosymbolic AI somehow to learn what's happening in XAI or something? Or you need to think of neurosymbolic AI from the scratch. So you have this problem, you have the data, and you need to start with that.
Not really. You can use a symbolic interpretation or a logical model, or you can find algorithms, or you can build a foundational tool to find or to explain a neural network-based system, if that's the question. You can, of course, use extraction systems, extraction rules, extraction algorithms, adapt, evolve them to use learning systems, okay, that were not specified as a scratch as neurosymbolic systems, and extract the rules, and then you can use this knowledge that you extracted exactly to improve the learning procedure for your next tasks later on. Okay? Yeah, you don't need to plan from scratch. And the advantage of getting old is that you never overcommit. Okay, I'm not saying that neural networks will solve everything or neurosymbolic will solve everything. I'm gonna say is that when one seeks semantics and needs to solve a well-founded problem that you need guarantees that you cannot compromise security or some other issue, then one should go for logic-based, symbolic-based techniques integrated with learning systems. Okay, that's crucial. Okay,
right. I have one now from Priscilla.
Oh,
Priscilla, I
great.
just discovered that you were the co-advisor of Leopoldo, and Leopoldo just joined my team here at Unicamp. Very nice to know. So Priscilla is asking, we humans many times first act or decide and then explain our decision. So how do you see this in the artificial world?
Very interesting. No, this relates nicely with system 1, 2. Okay, the analogy of the moment with that psychologists have studied for a long time, Kahneman. We decide very fast when we have problems that we have seen, we have a lot of experience about. In the artificial world, we are going to probably to take this reasoning or this principle to the tools that we are going to build, because we are building tools that no matter what they do, things more efficient than ourselves in image processing or other tasks. But when we're going to build tools that are highly sophisticated, including, of course, autonomous cars and so on, we will have to be more careful in implementing the so-called system 2, that is very reflexive in taking and training it to take decisions that are very balanced and very well thought. So I think, Priscilla, that this, let's say, impulsive decisions that sometimes we take, we have to think about not implementing them in artificial tools in AI systems. And by the way, it's a pleasure to see you here. I'm very happy because you were one of the first people in the world that, or let's say one of the pioneers as well in the 90s that started working on neurosymbolic techniques. So it's always a great pleasure to see you. Or not to see you, I'm seeing you virtually, or I am thinking that I am seeing you. I am imagining you, you see.
All right, guys. Luis, thanks a lot for your time. I know that you are very tired and it's the end of the day, but this discussion here today was very good, very bright. Thank you again for your time, for your presentation. I hope that you can send your slides.
Of course. Thank you to Marcos, who has thanked me, Jax, and everyone, all the friends here. Sorry for I always apologize at the end, because we know as teachers and professors that we can always improve. So sorry if I disappointed you. Okay.
No, it was very good. Thank you very much. And for everybody in the audience, thank you very much for your presence. Marcos, Jax, Priscilla, everybody else. Thank you very much. So guys, good night and take care. Bye-bye.
Bye.